Right. Take the next one. This is lateral displacement of fringes. Lateral displacement of fringes. This is the same as YDSE only. The YDSE only, but little extension. The same concept we have extended. And here this is the light source is there. And so imagine now here we have the two slits are there. Here we have one small slit S1. Here we have another slit that is S2. Now this light ray which is going like this and light ray will go like this. Right. And the light ray which is going here, this is straight away will go here. And at this location, maxima will be formed as we have seen at the center. Now, what I did now here, if I simply leave like this, now here at this location, we have maxima is formed. Okay, central maxima will call. But the thing is, what I did now here, so I changed the situation. Here, this is the screen. This is the screen. I have changed the direction now here. Ah, mhm. Now, so here in the path of this light ray, I have placed some slab or some object is placed, some glass slab I have placed. So that means this means instead of going for this light ray, this maxima will shift to some other location. Because okay, so when there is no slab now here at the the central maxima will be formed by placing some glass slab. The maxima will shift to some other location instead of going here. This light ray which will be shift to some other location like this, let us say here. So this central maxima shifted to this location. And here what I did now here, that is because of a glass slab is placed in the path, of this light ray. So this is some glass slab we have placed like this. A glass slab which I have placed like this. Having this is some thickness. The thickness is a T, and this will have some refractive index which is mu. Now this, instead of having the maxima here, the maxima will shift it to here. Now this is called as a fringes are displaced from here to O to P. This is called as a lateral displacement or lateral shift. Okay, that lateral shift we are going to analyze now here in this case. Okay. Now let's see one by one things now here. Because of placing this thing here, what happens, the fringes are displaced. So let's see this thing one by one points we will highlight now. Listen carefully these things. Now the path difference which will be equal to d sine theta, and which will be equal to, because of the shift. So this means it will becomes what element mu minus 1 into t. Mu is a refractive index and t is a thickness of a slab. And we have seen this thing as, and here this distance is shifted now. This distance which we are calling it as y, the distance with the slits and the screen, which we used to take it as capital D. Now from this, here we take it as a tan theta. Tan theta, this is from here to here. This is tan theta. So what is the tan theta will come to be now here? This is y by d. And this tan theta, which is approximated as a sin theta, and which is approximately equal to sin theta only. Then that should be given as, so that is d into sin theta equal to y by capital D, which is equal to mu minus 1 into t. Okay, from this we can say now y is equal to, this is capital D by small d into mu minus 1 into t. This is where y is called as a shift, is called as a lateral shift. Y is called as a lateral shift. Y is called as a lateral shift. How much the shift takes place now? This much. Right. Now, so sometimes we know this fringe width. Fringe width beta is given as what terminal? Lambda capital D by small d. Now this lambda to this side, if I bring now, this is beta by lambda, which will be equal to d by small d. In place of d by small d, I can place it as a beta by lambda here. So that means lateral shift, which will be also given as beta by lambda mu minus 1 into t. This is the lateral shift, beta by lambda into mu minus 1 into t. Okay. Now, so from this we can find this way. T is called as what? Thickness. T is called as a thickness. Now, thickness of the sheet is given by how much, you tell me now? Thickness of sheet. So that is given as T is equal to, we cross multiply now here. This is y lambda by beta into mu minus 1. This is thickness of the sheet. Okay. Now this lateral shift is independent of order of shift fringes. Lateral shift is independent of order of fringes. Any type of fringes, it is same only. Okay. Now this lateral shift depends upon wavelength. Here this lateral shift, why we have the lambda is there now, will depends upon the wavelength. Lateral shift depends on wavelength. Depends on wavelength. Okay. Next, number of fringes. Number of fringes shifted. That means how many fringes shifted. That is given by n is equal to lateral shift by fringe width. fringe width will give the number of fringes shifted. So that is given as what element of y by beta. This is a number of how many fringes has been shifted. Now this y value we have seen a y by beta. Beta will bring to this side. Then will come to be a what tell me now number of fringes shifted. Will becomes what you tell me now here. Number of fringes shifted, which will becomes as mu minus 1 into t by lambda. The number of fringes shifted will depends upon the wavelength. And here number of fringes shifted. So this is which is proportional to what element of 1 by lambda? 1 by lambda. So from this what we can say now here n1 lambda 1 which is equal to n2 lambda 2. So here n1 fringes are shifted for the wavelength of lambda 1. N2 fringes shifted for a wavelength of lambda 2. Then the relation is n1 lambda 1 equal to n2 lambda 2. Okay. Next. If a transparent sheet of thickness small t having relative permittivity relative refractive index mu r is placed in front of one of light beam. Then what happens now here? Then the lateral shift. Which is given as y is equal to d by small d into, then we can say this as a mu r minus 1 into t. Number of fringes shifted that is n, which will be equal to mu r minus 1 into t by lambda. Okay, in this case. And due to presence of transparent sheet due to presence of transparent sheet, the phase difference that should be given as delta phi is equal to 2 pi by lambda into mu minus 1 into t. This is the phase difference because of presence of transparent sheet. Okay. Next. Next. If the central bright central bright is shifted to, let us say, maximum nth maxima, then central bright is shifted to nth maxima, then in this situation this will be equal to then mu minus 1 into t, which is shifted to nth maxima, that is n lambda. Maxima condition is what, tell me now? N lambda. If the central bright is shifted to mth minima, then mu minus 1 into t, which is equal to 2 m minus 1 into lambda by 2. Okay. Next. If transparent sheet is placed, slit will call, slab will call, having some thickness. So by slab is placed in front of upper slit, then central bright shifts up. Okay, if a slab is placed in front of upper slit, central bright will shift to up. If I place in front of a lower slit, central maxima will shift to down. If the transparent slab is placed in front of lower slit, then central bright shifts down. Okay. Next. Now, if a transparent slab of thickness T1 and refractive index mu1, mu1 is placed in front of upper slit and a transparent sheet slab of thickness T2, refractive index mu2 is placed in front of lower slit. Then the condition for central bright should not shift. It is This is mu1 minus 1 into T1, that should be equal to mu2 minus 1 into T2. This is the condition. So that's we have placed the here. If I place a slab in front of upper slit, will move up, lower slit will move down. But if I place the slab in front of upper as well as lower, but central braid should not move. For that, this condition has to satisfy. Mu1 minus 1 into T1 equal to mu2 minus 1 into T2. Okay. Next one. Shape of interference fringes. What type of shapes we can form? If S1, S2 are the two slits, then the shape is what are known as straight fringes. If S1, S2 are the 2 point sources, so these are the family of hyperbolas. If the screen is perpendicular to the line joining the two sources, then the shape is a concentric circles. Family of concentric circles. Okay? The shape of the interference fringes they may ask in the problems. Diffractions. Diffraction. So diffraction means there is a difference in the analysis of interference and diffractions. Diffraction means bending of a light. Generally, what we assume now here, light will always travels in a straight line, isn't it? Now, so let us consider here we have taken some slit we have taken, and here this is the screen. Here we have placed some screen we have located. Now, so we used to consider light will always travel in a straight line, right? Now here the light rays are coming, just imagine the light rays are coming from here. Light rays are coming here. Okay, these light rays are coming like this. These are the light rays which are coming like this. Fine. So this light ray which is along this path, this light ray will straight away will go like this. Will hit here. But this light ray which is at the edge of any obstacle, this light ray, what we expect now basically, this light ray, so it will simply straight away will go and will reach here, isn't it? That what we expect. And this light ray which also will go like this straight away will hit here, isn't it? Now, so what we expect now here, this region we used to expect it as a bright light is falling now. This we expect is a bright, and the remaining part is completely has to appear dark. This we expect it as a dark, and this part is also we expect it as a dark we expect, isn't it? And only this part is a bright. This part is bright, but it won't happen. It won't happen. So here, when it doesn't not happens now here, this gap is there now if the distance is d. So if the d if it is very much greater than lambda, then so the light straight away you can see now. But if the d is not very much greater than lambda, then in this case, what happens now here? If the d is comparable to lambda, in those cases, the light ray will show one special property. We expect the light ray will hit here, but in this case, light ray will bend like this and will hit here. Understood what I am saying here? Instead of going this light ray here, this light ray will go here, and this light ray will hit here. So as a result, if the light ray is falling now here, so from here to here will appears as a bright hole in this region. Actually, what we expect now here in this part, here we expect the shadow region, that is shadow has to fall. But here shadow won't fall. So this still this region, this complete region is a bright only. And this phenomenon is called as a diffraction. If the d is very much greater than lambda, so the diffraction is not possible. No, diffraction is not observed. No diffraction in this case. Now, in this case, only diffraction we can observe. Understood what I'm saying here? Huh. So this bending of this light ray, when there is an obstacle is coming, this phenomenon is called as a diffraction. Okay. And here we have the two types of diffractions we should talk now here. One is called as a Fresnel and Fraunhofer. Two diffractions are there. Yes. This is one is a Fresnel and Fraunhofer diffraction. So this phenomena. The phenomena of bending of light at the edges of the opaque obstacle and spreading into the geometrical shadow region is called it as a diffraction. And diffraction is a characteristic property of a wave. Electromagnetic waves, water waves, sound waves will exhibit diffraction phenomena. When the slit width is comparable to wavelength, then only we can able to observe the diffraction is observable. And diffraction depends upon the width of the slit and the wavelength of light. Okay. And the two diffractions we used to talk now, one is called as a Fresnel, the other one is the Fraunhofer diffractions. And so the difference between the Fresnel and Fraunhofer diffractions are, so in case of Fresnel means small distance, Fraunhofer is for the large distance. In this case, the source and screen are at finite distance only. These two are finite distance. So that's why here you can observe the spherical or cylindrical wavefronts you observe. In case of Fraunhofer, that is infinite distance are there, source and the screen. And since it is infinite distance, what type of wavefronts we have formed? Plane wavefronts are formed. In this case, lenses and prisms are not required, but here lenses and prisms we use to make that practically the object is infinite distance. It is not possible. By using the lenses, we can able to make sure that object will appears to be a infinite distance. As we know, if the object is at the focus, then what happens now? Image will form at infinite distance now. So by we use that property here. Yes, here the distances are important. In this case, angles are important. Okay. Now in the diffraction, so the when you're coming to the diffraction formulas and the YDSE formula, so do remember at the in case of a maxima formula of interference, that is YDSE, in the diffraction is minima. Minima formulas are maximas, keep in mind. The formulas of diffraction maxima case. Earlier we have seen what the condition to have a maxima here. So here d sine theta must be equal to n lambda. But that is now that is a minima case. And minima conditions will come under 2n minus 1 into lambda by 2. Here that is 2n minus 1 into lambda by 2. This is for maxima case. Yes. And another important thing there we have seen the fringe width, we have seen a beta which is given as lambda capital D by small d. In case of diffraction, in case of a YDSE, all the widths are same. Width of the each fringe is same. But in case of diffraction, central fringe width of central maxima is 2 times the beta. 2 times we have. Remaining will be little bit normal beta only. Okay. And angular spread is also 2 times. That is 2 lambda by d. And the intensity relation is I is equal to I naught into sine square alpha by alpha square. Now these are the formulas for in case of a diffractions. Okay. The major thing you need to remember here, it is what, tell me now? YDSC maxima formulas, here it is a minima formulas and vice versa. Minima will come maxima, maxima formulas will come minimas. Okay. Yes. Copy these formulas. In case of a diffraction, the intensities which will be like this. Intensities, the variations is like this. Central maximum intensity is high. This is central maximum, and the remaining intensities are goes on decreases like this. Like this rate goes on decreases. Here this is central maxima. Here the intensity which is I naught. Here this is lambda by A. At the lambda by A location minimum. So that is 2 lambda by A. Next we have 3 lambda by A. This is minus lambda by A minus 2 lambda by A minus 3 lambda by A. Now here we have the intensities there. Now this is 4 by 9 pi square into I naught. Here this is this intensity which is equal to 4 by 25 pi square into I naught. And here this intensity, this is 4 by 9 pi square into I naught. This is 4 by 25 pi square into I naught. We'll get the intensities like this. Yeah, once they asked this question also, intensities. Intensity ratio they asked. So that's why you need to remember this also. Right.